heat concepts. We're going to talk about heat transport, hopefully, at the end of lecture today. There'll be some homework over the weekend, but I want to do a grading update with you and then also review the brain burner from chapter 11. So let's go. Just to remind you, there's SI right after class today, 12:30, and I've been hearing from both of my classes that SI is really helping people, and I hope it's helping everybody here that goes. Monday also a session, so hopefully you'll be able to wrap up your homework over the weekend at SI. I want to go through some grading estimates that I published yesterday morning, so that if you were worried about the W deadline, you can relieve your mind about that. So let's go over the specs for grades right now. We have exam 1, so you have some number out of, almost everybody has it, something out of 50. Exam 2, similar, something out of 50. Those are on the books already. You should easily be able to look those up in your grades page. Now the homework converts to 25 out of 25 points in the grading. And right now, or I should say, as of Tuesday, we had 10 assignments and 103 points. So the grades that I published and the homework points that I converted to were based on homeworks 1 through 10. Now, and that's because homework 11 was still running, so I couldn't put those points in there. Anyway, so that converts to something out of 25. Clicking also, and we've had 34 clicking items. So the 85% level, can somebody double check this? 29 divided by 34. Can somebody check that on the calculator? 29 divided by, I think that's the first whole number above 85% of 34. 29 out of 34, what do you get? 85 something? Okay. Yeah, so if you have 29 points or more, you're automatically 25 out of 25 for clicking. So total of 150 regular points possible. Now, as a side note, some of you, and I was talking to students about grades yesterday in office hours. It's 100% normal, especially this time of semester. There's a few bonus points on the books right now. And actually, there's some bonus points in exam 1, I think, that some of you took the time to get. And no, I take that back. That was for my online class. But we have early iClicker registration bonus points, 3 of them. Some of you have them. Some of you are supposed to have them and don't have them yet. So if you don't have them yet and you know you're supposed to, I got a bunch of people to update on that. Don't worry. But as far as 150 regular points, yeah, everything's on the books. Now, this is going to be the grading scheme for us until the final. That's another big 100 point. But we have another midterm ahead of us. But that doesn't add another 50 points, because when we've done all 3 midterms, then we take the best 2 scores that you've got. So we still have something out of 50 and another something out of 50, whether it's exam 1 and 2 or exam 1 and 3 or exam 2 and 3. That's up to, how your scores rack up. But eventually we'll be hitting the final. But for everything that I talk about today, you'll be able to do until the end of the semester. And then after the final, you just look at the syllabus, the points total on the syllabus. All right, so right now, if you look in your grades page, you'll see at the very top, if you go by assignment group anyways, total points as of 3/19. So this John Q student here has 121 out of 150, right here. So now that's composed of, like early iClicker registration points, and here's the homework situation. Now this student had 92 out of 103, so we just go straight percentage and then round up to the next whole number. So that means, this 92 here converts to a 23 out of 25. And that's what goes in with his exam scores. So I don't put 92 in with your exam scores. I would put in 23 for the exam scores. And you can see homework 11 down here at the bottom is blank for the John Q student when I did this grading printout. Okay, the roundup figure that I published yesterday morning, something point something something, and as always, the number of answers that you have submitted is in the decimal part. This is a compact way for me to tell you how many you've answered, in this case 33, all right? And also it encodes how many you've gotten correct. So this John Q student got 31 of them correct, so he's blazing, whoever that is, right? But the participation pointage goes out of how many you've answered. This is the one where if you have 29 or more, automatically you're at 25. Now this guy's an automatic 25 because he's way above 29 answers. Okay, so now for those of you that are below 85%, and all you got to do is, you know, your answers divided by 34, and is it below 0.85 or not? If it is, just review lecture 12. We went over how to calculate that. Lecture 12, I think the baseline was 17 points. Now we've got 34 points on the books. So that is changed, but use the same proportion. Just go back to lecture 12. And here's a screen grab from lecture 12 where we talked about, yeah, 17 points, 17 questions. All right. And we worked that out in lecture 12. So go ahead and review that if you need to. All right. So as I say, check your total points as of 319. And then go and look at this table. Now, I put this table in discussions and also in announcements. It looks a little different, but it's basically the same table. And this is the 90, 75%, 90%, 75%, 60%, 50% splits for letter grades, but for the 150-point basis. Now, on the syllabus, you have a table similar to this, but for the full semester, 250-point basis. So for the rest of the semester, until the end of exam week, when we hit the final, you can always calculate your grade and look at this, all right? And for reference, it's in web courses. Now, if I were giving letter grades today for the semester according to this table here, this is how they would stack up. Now, I want you to look at that. This is the curve, the distribution of grades. There's 10 A's, 54 B's, 31 C's, 7 D's, and 0 F's. So we got a ton of B's. So people are doing pretty good. But you know, A's, it's, you know, A, you got to work to get that. Now, hopefully, we'll, you know, boost that up by the end of the semester. This is just, you know, this is a snapshot in time. At the end of the semester, hopefully you guys will crush a few more exams and get yourselves up. I want to push as many of you as high as possible on this curve. I want to break it. That's why I never grade on the curve, because I always get the students to break it. With this, you know, if I forced the grades into a curve and graded by curves, I'd be ripping off all the people up there at the top end of the curve, you know, and so I never do that, right? So my job is to convert all you guys into brainiacs and break this curve. And if you all get A's, you'll all get A's. I'll put it on your report card, no problem. I have no problem giving out A's if you earn it. All right. Now, one thing I want to point out, this is not the entire class. This is only the grades of only the students that have taken both exams. Now, students that haven't taken both exams, they're not going to be on this. You know, and that's mostly people that didn't take exam 1. It seems everybody took exam 2, which is good. All right. So if you didn't take exam 1, You won't be on this table until after exam 3, and then you can, this is an interesting fact. Nobody in here that has taken both exams is failing, right? Now that is why that is one reason I never grade on the curve, all right? I control your, I control your guys. I try to be generous with grades, but tough. So this is a case where you can see we're generous with grades in terms of students that are in class faithfully and clicking faithfully and doing their homework faithfully. They're not down there in the F's. They're somewhere up above there. Most of them are up in the C's and higher somewhere. All right. And so you can see from this that the class, if you're here for all the exams and all the classes, it's tough to flunk. But yet, it's not, it's tough to get an A, and that's the way it should be. I think that's fair. Of course, I want to populate the A column a little bit more, and we will. Some of you guys are, and if you look at your total points, you'll know that there's at least 2 students with 134 instead of 135. So they're right at the borderline. And if you're in the 120s right now, you are in striking range of an A, my friend. All right, if you continue to work hard. So, all right, now questions about this stuff. Let me go backwards here. Any questions about this, the grades and stuff? Okay, well, that's good. Let's review the brain burner from homework 11. Now, you may have a feeling about the brain burner. Here it is. This is the instance of question 9, and I took this out this morning. Mass of 7 grams of ice. Initial temperature, everybody started at 268. So delta T is for heating up the ice is 5K, I think, for every example. The part that changes is the final temperature. The mass, I think it's the mass and the final temperature. And so this one, the final temperature was 276. So that means your second delta T, when you're heating up the liquid water, is 3 kelvins. Now, you might have had one that's 8 kelvins for the second delta T, and you just got to calculate with that. You got to read carefully. And both of these specs go into this. Let me get my cursor over here. Come on, cursor. Where are you at? There we go. Okay, so here's the heating up equation. Q equals mc delta T. M the mass, C the specific heat, and we're going to go over this calculation in a second. And delta T, the change in temperature. All right, here we go. Here's the specs. You can go ahead and jot these down. And this is the one for this example with the 7 grams. Okay, so heating up the ice, mc delta T, mass is 7 grams. And in the big parenthesis in the top equation block, 0.50 calories per gram Kelvin. That's the specific heat for solid water, i.e. for ice. And then the delta T is 5K. So that works out to 17.5 calories. All right. And that will get you to the melting point. Now, at the melting point, when you're melting 7 grams, you're at 273 through the entire process, but you still have to add energy because remember, energy is like going in there and busting up those crystalline bonds of ice, metallic bonds if it's a metal. So 7 grams times, the figure for ice is 80 calories per gram. That's, so a gram of ice is a certain number of molecules of H2O, a certain number of pairs, hydrogen bonds between pairs of molecules that you have to break up. So It's a certain number. And if you go on the gram, you could go on molecule by molecule basis. And I think there's probably a way I'm sure there's a way to calculate that. But on a gram for gram basis, it's 80 calories per gram. So just multiply by how many grams you got? 7. 7 times 80, 560. All right. And then the last one is, all right, you've melted it all. It's at 273, and you got to bring it up to 276. All right, so this is Q equals MC delta T again. Oh, by the way, that symbol up there in the middle equation block, Q equals M times L with a subscript F. That's not L final, that's L fusion, latent heat of fusion, which is the fancy scientific name for freezing. You wouldn't say that copper freezes when it becomes a solid. You would say it fuses to become a solid. If you're in the chemistry department, that is. But anyways, so getting back down to the third equation block, liquid water. Yeah, Q equals MC delta T. The same number of grams. Now this is assuming through this whole process that you haven't leaked out any of the water. Okay, if you have a leaky stove or something, maybe you're going to, but this is assuming, you haven't leaked out any water or anything like that. So still 7 grams, but notice in the big parenthesis in the equation block, it's 1.00 calories per gram Kelvin. That's the specific heat for water, right? Liquid water. And we're bringing it up by 3 Kelvin. So that's a total of 21 calories. And so the answer works out to 598.5. And I asked you to give it to the nearest whole number of calories. So that would be 599. All right. Now, if you don't believe me, look at this next slide. All right. Now, this is after I submitted that with the answer 599. So here's the answer down here in the lower left. Ching, 599. And up here in the upper right, you can't see it maybe, but that's 3 out of 3 up there. So I got that one right. So this is a good answer. All right. And just to reinforce, here's a picture of Bruce Lee, famous for busting things up, crooks and stuff like that. Latent heat is the work needed to break apart bonds, whatever the bonds are. Covalent bonds from some kind of solid, hydrogen bonds for liquid, for water crystals, so forth and so forth. And it's rated in calories per gram. You could go joules per kilogram if you wanted to, but we're gonna stay with calories per gram. Now, we just reviewed the brain burner, and so Salam, what we're gonna do now is we're gonna practice one. Let's see if you guys can do it again. All right, so let's do a little practice with some H2O ice, and we're gonna heat it up. All right, now, I see a lot of people sitting out and nobody's sitting next to them. Now, I'm not going to say anything about it, except that it makes it harder to talk with your neighbor and coordinate on your neighbors with the next clicker question. Did you have a question?
Yeah, just on the picture before, I just don't know if you got the second from, or maybe I just overlooked it.
Here? Yeah, let's go back. It's the final temperature is 276, and the initial temperature is 268. All right, so you're starting down here at the cold temperature, going up to 273. See, if it's water, you're always oriented to the melting point, 273. All right, so this is 5 kelvins below, and the final is 3 kelvins above. All right, so that's where that 3 kelvins comes from. All right, so yeah, so Dr. B, I scored on this one. By the way, number 8 was like a simple heating up, like the first third of this problem. So number 8 was similar to that. Okay, here's Bruce Lee. All right. Now, this is going to be, let me adjust this. This is going to be a numeric answer. And here's your question. 120 gram chunk of ice up in Greenland. Initial temperature 260. And you want to get it up to 300. So you're not going up to 373 or anything. Just 300 is good enough for drinking water. So calculate the energy budget for this process. Right? So work with your neighbor or by yourself if you like, and just work it out. Let's see how you guys do on this one. And while you're doing that, I'll consume some drinking water. 300 minus 1. No, it's going to be a big number too. It's going to be a pretty big question. L subscript F is a property of water, and it's 80 calories per gram. And it will be, I'll put that on the cover page of exam 3 if we need it. So, so it's not something we get to memorize. I mean, I know it, but because I use it a lot, but I don't like hearing that cough over there. Are you sick or something?
Not at all.
Oh, so this thing, you got 3 different calculations. What? He's a helpful lad. It's kind of like me trying to help my wife in the kitchen. I'm so helpful. She says, "Okay, you don't have to help anymore." She just boots me out of the kitchen so I don't mess things up too badly. I know I know how to make certain things in the kitchen, but what's that? Yeah, yeah. That's what I do when we have cookouts at my house. I usually do it. I use charcoal too, not that phony gas propane stuff. Okay, 1 minute. 30 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Don't forget to hit the send key. If you got your answer, make sure to hit the send key. Good, I got a couple more there. All right, let me take a look at what you guys got. Oh my goodness. Oh my gracious. Raise your hand if you. Oh, wait a minute. Let me stop the question before I give you the answer. Okay. Raise your hand if you typed in 13620. Sweet. Nice. Got a lot of geniuses in here. All right. Now, um, so there's your answer for this doozing polar bear up there. Now, I want to continue. I'm glad you did a good job on that. And if you got tripped up on it, you know, talk to one of your neighbors or maybe at SI, maybe you guys can review. Deanna, question. No, because a delta is always a subtraction, okay? And in this case, it's later minus earlier, okay? So 273 is later than 268 because you started 260. So it's 273 minus 260. And then the later one for the second heating up process is 300. So it's 300K minus 273K. All right. So yeah, deltas are always, now there's some things that we do, you know, like moment of inertia, that's a sum. You know, that's adding stuff up. But deltas, always a difference, always a subtraction. All right. Now I want to do some more thermodynamic concepts with you, specifically about the kinetic theory. Um, you know, we've transitioned in the past week from basic dynamics, you know, of circular motion, angular momentum of a planet. And now what we're attacking are massively populated systems. You know, systems where you know, this is, if you look at this cloud, every bit of that cloud that you see, you know what that is? That's liquid water. Those are droplets of water. That's not water vapor. It may be surrounded and you know, mixed with water vapor, but what you see is tiny micro droplets of water held aloft by the, you know, the updraft. That's a thunderstorm coming over the mountains. out in California. It's a famous photo here. So I want to talk about this kind of transition from everyday things, like the Ferris wheel and box cars and stuff, to these systems with enormous populations. Like here's the aurora borealis seen from space, and that's a bunch of atoms and molecules in the upper atmosphere is getting blazed by stuff coming in from the sun and getting trapped by the magnetic field of the Earth. So one of the things that we assume about matter is that gas itself is considered a collection of molecules or atoms, and that there's a huge number of them, and they're far apart from each other. They have a random distribution of speeds. It's all hervy-turvy, topsy-turvy. But there is a pattern we have found. They ricochet like BBs from each other and from the walls of the container if it isn't a container. And you know what the container is? The Earth, the gravitational field of the Earth contains our atmosphere. So it's not a rigid wall or anything like that. So for the atmosphere, the containment is gravity, but they can go through that. And in fact, a lot of stuff, we don't have a lot of hydrogen in our atmosphere because it zips around. It's so small, it moves so fast, it can escape the gravitational pull of the Earth. Helium as well. But oxygen is big enough to stay on Earth for the most part. So they ricochet around without much interaction other than, bouncing like BBs or billiard balls off each other. And then, we believe, we have a rational belief that they obey F equals ma and everything else. Newton's 3 laws of motion, etc. Okay. Now, therefore, they have kinetic energies, and as if you did your reading, you know that the whole strategy of the kinetic theory is to assume F equals ma for a zillion little particles and stuff, and then kind of use stats and calculus to figure out the properties. So the kinetic energy of molecules in the gas, they have a huge range from slow to fast. But if you apply calculus and trig to it, you find that the average kinetic energy is proportional to the absolute temperature on the Kelvin scale. And so that's the kinetic theory. And one of the things that I want to talk about with you today is this random distribution of speeds. It's very, very important. And let's go ahead and take a look at that now, if I may. And if you don't have everything copied down, remember, you can go to YouTube and pencil stuff in after class. So let's talk about that distribution of energies and speeds. It forms a curve. And here's the curve that it forms. So the vertical scale is the number of particles, and the horizontal scale here for this one is the speed. All right, so over on the left is slower, and over on the right is faster. And so what this curve tells you is that the most probable speed, the one where you have the most particles, is kind of here in the middle at the top of this curve. So that's your peak speed. The average is actually going to be a little bit to the right of that because it's not as symmetric. And when we say it's not symmetric, take a look at this. Over here on the left side, the curve is a little steeper. So this is like a mountain. And this side of the mountain is steeper. And then this side over here, steep, but it's not quite as steep. All right, so it drops. And so so it's not perfectly, like a Mount Vesuvius type volcano that's pretty much the same angle all the way to the top, unless it blows itself up and then it's, blooped up and stuff. But this one's kind of anti-symmetric. All right, and let me get that out of the way. And what we found is that the distribution of speeds, modeled by this, and you can label it meters per second across the bottom if you want, and it's just plain old number count on top. It differs, and hopefully this makes sense to you. It differs by temperature. Remember, the temperature is proportional to the average kinetic energy. So if you have a high average kinetic energy, that means you have a lot more stuff to the right side of this graph, right? So now here's what two different temperatures look like. One is 2000 Kelvin, the red one, and one is 273 Kelvin, all right? Now there's a lot more, and this one, the speed is rated in meters per second, m times s to the minus 1. That's the same as meters per second. The red curve has got a lot of stuff off to the right at higher speeds. And the blue curve, the greenish blue curve, 273, that's the boiling point of, or the melting point of water. That is, or 0 Celsius. That's got a lot of stuff down in the low speed, and it's a much tighter curve as well, all right? So the peak of this distribution changes with temperature, right? So we would say that it's temperature dependent, all right? Now, here, and look at that formula down in the bottom. That's part of the graphic that I stole from, I don't know, Harvard website or something like that. Look at that thing. The probability density function for speed is a big square root out in front, or that's a square root of a third power, and then e to the minus blah blah blah. That's like logarithms and stuff. And so don't worry about that. It's gruesome. That's what we call an exponential function. And it's not that bodacious, but it's a little bit more than we are going to do in this class. So you can take a look at it and remember how nasty it looks, and just remember nasty. And then, but I don't have to calculate with that jazz. All right, so we have this temperature dependent distribution of speeds and energies. This one's the speed distribution. And what we're going to do now is talk about a guy named Max Planck, because he worked with this distribution that was developed by a Boltzmann, a German scientist. And Max Planck is also a German scientist. And he savvied the situation with all of this. And so here's a picture of Max Planck. And what he figured out was this relationship between color and temperature for incandescent objects. Like I said before, some stars are red because they have a certain surface temperature, and our star is kind of greenish yellow because it has a higher temperature, 5,800 Kelvin on the surface. And nobody could figure it out until Max Planck figured it out. So let's talk a little bit about Max Planck. Very famous guy. He was a theoretical physicist in Berlin, Germany in the 1890s, and he was very interested in thermal physics. And he especially was interested in the strength and wavelengths of the entire spectrum of electromagnetic radiation that was produced by something called a black body, a theoretical object or construct, which is hypothetically a perfect absorber of radiation, so it doesn't reflect anything, and so that's why we call it black. But also, it's a perfect emitter of radiation. So it's perfectly, there's no energy lost. Whatever it absorbs, it's also going to emit back in form of black body radiation. All right? And this is related to the speed and energy distribution we saw a few minutes ago. All right? Now, this black body radiation, here's a set of black body radiation curves. All right? Now, I want you to understand what the vertical scale and the horizontal scale are. The horizontal scale is the wavelength in nanometers, nm. And right here, from 400 up to 700 nanometers, that little green window, that's visible light. Visible light is in that wavelength range. Below that is ultraviolet, and above that, you know, at 1,000 and 1,500, that's infrared. And what scientists were able to do, and I've actually done this, you take an oven whose temperature you can control carefully, and then you basically put a photo detector, you know, like a photo cell, and that you can tune to pick up the energy from different colors. So you get a photo detector that picks up red, and you get a photo detector that picks up green, and a photo detector that picks up blue, violet, ultraviolet, back down in infrared. And then you just pile up, you know, on the vertical scale, how much energy you get from each color, right? So the red curve is getting an awful lot of energy in the visible band. And it's getting some energy down here in the ultraviolet, the low wavelength. And it's also getting a lot of energy out here in infrared. And that's for an object. What is the temperature of that? Does that say 5,500?
Yeah, the first one.
Yeah, 5,500. So that's almost the temperature of our star. And that's what we get. We get a lot of our light in the visible band. Now look down here. This bottom curve, this one peaks outside of the visible band. All right? It's a blackbody curve, and it peaks outside the visible band in the infrared. This is an infrared star. And you know, Betelgeuse, the one that we looked at the other day, possibly looks like this. Visibly, we see a lot of red. The brightest color inside for this last curve down here, the black curve, the brightest color is red. Out here it's 700 nanometers. This is the red end. And then the 400 nanometers, that's the violet end. Anyway, so the brightest color of Betelgeuse is red, but the actual brightest of all the wavelengths is infrared. So Betelgeuse and stars of that surface temperature are going to be brightest in the infrared. Now, nobody knew why this was the case. All right? And, you know, we have 5 black body spectra, 5 different temperatures. Nobody could predict the shape of the spectrum based on, you know, electromagnetic theory and thermal physics until Max Planck started working on it about 120 years ago. All right? So these are black body spectra, and those are spectra of huge, like stars, huge collections, huge populations of hot hydrogen. You know, so hot that it glows at, you know, in these colors. So let's go back to Max Planck's outline here. In 1900, so that's 119 years ago, he wrote a new theory of black body radiation. He savvied the whole problem there. Nobody could get a bump. Everybody could get something going up to the left or going up to the right, but nobody could get one that goes up on the right side, hits a bump, and then goes down on the left side. Nobody could get that until Max Planck did. So here's what he said. He quantized the energy, and that means that the energy of the oscillators, the electrons in the object that were emitting the light, had certain energies and no others. So they came in bundles of energy. So it's like money. You know, money for us in America is quantized into cents, pennies. Okay, you can have any amount of money, but it's always going to be a certain number of pennies equivalent. Now nobody goes around with pennies. Uh-oh, battery is low on my earphone here. So nobody goes around with pennies unless you're going to Walmart and trading them in for, you know, bucks with that machine that they got. But that's what Max Planck said. Assume the energy of all the radiators in a black body radiator have certain multiples of energy. And to introduce that energy, he introduced a constant called Planck's constant, H. The symbol is H. And with this, he was able to do what nobody else was able to do. He explained the spectra peak, the way that they behave by temperature. Okay? And nobody else was able to do it until he did. And it was by introducing his constant H and the quantization of energy. And so this was actually what Max Planck did here in trying to understand the thermal physics of huge populations of things like stars or blackbody radiators. He was able to actually start the quantum revolution. He started it. And we're still in the middle of it. We're still trying to savvy as many things as we can about quantum systems. Now, one of the things I want to review with you is some more electromagnetic peak and temperatures. Okay, so room temperature, conventionally known as 290 Kelvin, actually has an infrared peak. All right. The human body, 310 Kelvin approximately, infrared peak. Now, the reason that, that means that everybody in here, we could turn off the lights and everybody here would be invisible unless you put on infrared goggles. And then you can see everybody, because everybody in here is going to be emitting plenty of infrared. So the main color that you emit is infrared. Now, you don't really emit much in the visible band. The reason that, you may have a red shirt or a blue shirt is because the light from the lamps here in the classroom bounce off your shirt and then come into my eye anyways. The red ones, it absorbs everything except red, and red's reflected, and that's why a certain thing will look red. And I see somebody in the back with kind of a greenish aqua shirt. Okay, it looks very nice. It's almost whitish. So if something's white, that means it reflects all colors. So that shirt back there is kind of a light bluish aqua. It's reflecting almost everything, but everything other than green and blue, it's not reflecting as much. It's reflecting more green and blue than anything else. But green, red, yellow, orange, and those colors are still being reflected, just not as much as green and blue. All right. So the human body, produces that all the time, and until it gets, covered up, then you can't, if somebody cover, if you go inside a building, you can't see a human usually. Standard temperature and pressure, 273 Kelvin, infrared peak. That's for the chemistry department. Mount Everest on a cold night, 238 Kelvin. Whoop, you're freezing your you-know-what off. Infrared peak. Now, the surface of the sun, as I mentioned before, 5,800 Kelvin, that's way up there. The sun is basically a gravitationally contained hydrogen bomb. It's fusing hydrogen. This is the way that our nuclear weapons do, except it's so big that gravity, it doesn't explode out into space, but it still gets mighty hot. And it's got so much hydrogen, it's going to keep fusing hydrogen for billions of years to come. But at the surface, it's 5,800 Kelvin. And so that's kind of a greenish, yellowish peak. All right, now we're going to talk more about Professor Max Planck in a few weeks. But right now, what I want to talk about is our next topic, which is heat transport. Now, raise your hand if you've ever seen one of these guys, a fire breather, doing this. Raise your hand if you've ever seen that. A few of yous. And of course, you can see it on TV and stuff, and Discovery Channel and whatnot. But I love this picture because it shows all three of the heat transport modes. It shows radiation, it shows convection, and it also shows conduction. All right, now I'll show you how that works in the next few slides. First of all, conduction. Conduction is heat that's transferred by physical contact of hot with cold. So heat flows into the cooler object relatively easily. So that means kinetic energy is exchanged between the two objects, if they're gases anyways. And you can see that here um, in this photograph. This fire breather, he has to have that little side torch. You know, he puts kerosene or whatever it is in his mouth, and he blurps it out as little tiny droplets and some vapor, but it's not burning inside of his mouth. He has to touch it off with that little torch, and then it moves off like you see in the photo. So it raises the temperature of the cooler object, and it cools the temperature of the hotter object. So there's transport of energy. It's basically a lot of kinetic energy getting transported. So the fire breather has to use a torch to light up the kerosene because it can't be so hot. It can't be hot enough to burn while it's still in his mouth. So it's cool in his mouth, and he's got to light it up after it leaves his mouth. So now a counterexample to that is an insulator. So an insulator is something that doesn't conduct heat very well, right? So that torch conducts heat into liquid kerosene pretty well, pretty efficiently. Bam, it's lit up, right? Which makes it exciting. But styrofoam, it's a good insulator. Your ice water will stay cold and nice, for hours if you have a good styrofoam. Like this, this water bottle up here, is that a fancy water bottle? Somebody left? I see millions of water bottles up here in the front people leave behind. Anyways, so a water bottle like this is well insulated, a little bit of styrofoam or something. And so stuff will stay cool or it'll stay hot. If it stays cool, that means heat is not coming in from the outside. If it stays hot, that means heat is not going out to heat up the outside. All right? So that's conduction, physical. And here's another example of conduction. You putting your hand, you putting your hand on somebody's skin, they say, ooh, you have cold hands or something like that. Or you squirt out a little bit of ointment on your arm and it feels cold. That's because your arm is heating up the ointment, or your arm is heating up your friend's hand if they feel like they have cold hands. But what they say, cold hands, warm heart. So that's not too bad. Okay, convection. Now, convection is a process of bulk motion, right? Conduction is a process of zillions and zillions of little kinetic theory molecules carrying kinetic energy from point A to point B, from one substance to another. Now, bulk motion and convection is basically this. If conduction is not rapid, you can get bulk motion because the hotter stuff, if you have it, is usually less dense. So if it's surrounded by a cooler fluid, like this guy's got a fireball of kerosene, and it's surrounded by the ambient air, which is, the kerosene is really hot, right? I mean, you'd burn yourself if you stuck your hand in it, right? And so, but it's surrounded by regular room temperature air, wherever he is here. Okay? And so that hot stuff is going to have a buoyancy force upward. Okay? So the fireball is going to rise upward, and that's why and all the pictures that we've seen show convection of fireballs upward. Notice that he tilts his back so that he's blurping out his kerosene so that it goes straight up. And notice he's got a couple torches left and right there. Yeah, so this is conduction as well. But yeah, the fireball going up there like that, yep. Now, here's an interesting fact. The mantle of the Earth, all the boiling molten lava and stuff, and the rocks and under, if you get a certain depth, the rocks actually become like a fluid, but it's a very viscous fluid. It's very stiff. all right? But it does, I mean, it flows, all right? And one thing that we've been able to find is that underneath, for instance, Yellowstone National Park, there's a huge plume of heat um, blobbing upward by convection from the mantle, from the the mantle, the top of the mantle of the Earth, right? And that's why Yellowstone is such an active, like old faithful the geyser, and it's actually a volcano, and that blew up a super volcano. They say that blew up, thousands and thousands of years ago. Last time it blew up was thousands of years ago. So it's not really volcanic right now, but it's still thermal because of this Yellowstone mantle plume. Now here's a side view. Basically what we do is we get a bunch of seismographs. Yellowstone's got zillions and zillions of little tiny earthquakes all the time. I used to live out there when I was in grad school, just 40 miles away from Yellowstone. And I know that the seismographs that they had at Montana State, every day picking up little miniature, nothing, really big. Occasionally something, every 10 years or so they'd get a big earthquake. It, was, cause a landslide or something. But thousands and thousands of little tiny. So what they do is they analyze. They set up seismographs all over the place. It's like sonar. A seismograph is picking up sound waves in the earth. So whatever the Navy does with sonar to locate, enemy subs and stuff like that, that's basically the same technology that they're doing here. So what they look for is slower seismic waves. So, and that's what the Navy has to do as well, because, the speed of sound in water depends on the pressure and also the temperature. So if you get a really cold, and also if it's salt water or fresh water. So if you're out in a submarine where a big river comes out, dumps out into the ocean, you got a lot of streams of fresh water mixing with salt water, and it screws up your sonar performance, or at least you got to know how to handle it. Anyway, so the slower seismic waves, they slow down when they go through the mantle plume because it's hotter. If it's hotter, that means it's more liquid. All right, it's less rigid. Now, if something's really rigid, if you take a railroad track, now don't go out and do this. But I'm just saying, if somebody did this and they put their ear to a rail of the railroad track, and then somebody a mile away banged on it with a hammer, you'd hear it within seconds, very fast, because the steel would transmit that sound pulse down along the rail, chop, chop, all right? Versus air, you wouldn't even hear it. It would dim out. You wouldn't even hear it if it was a mile away. So some guy a mile away hammering with a hammer on a railroad track, you can hear it if you have your ear to the rail, all right? Or like in cowboy movies, somebody puts their ear to the ground. Oh, I hear buffalo 14 miles away. I heard a buffalo. Let's go get it. And that's through the ground, right? And I guess that's possible. I've never tried that, but definitely railroad tracks. So basically, you've got dense and less dense, rigid and less rigid. And if you analyze your data, like the Navy does for submarines and stuff, they can even figure out the temperatures. So this picture on the left is one view. That's a cross section from northwest to southeast, and the other one is northeast to southwest. So they look a little bit different because you're looking at different poses or different angles at it. But yeah, that's the Yellowstone mantle plume blazing up from deep down under the crust of the earth. And where there's another one? Hawaii. Hawaii's, all those volcanoes out there. Way out in the middle of the ocean. Yeah, it's a mantle plume of some kind. So let's keep going. So the three modes of heat transport. The next one is radiation. All right, now, I alluded to this the other day. Radiation, momentum and kinetic energy are carried by photons of light. A photon of light is the quantum of energy associated with the electromagnetic field. Right? It was a concept developed by Albert Einstein, the photon. And photons of light are any, so radio waves, X-rays, we can associate photons with them. They carry momentum and kinetic energy from point A to point B. Now, if they intersect with a material that absorbs it, glass won't absorb a whole lot of visible light. So, visible light, if it's a good quality glass, will go through it. But, glass will heat up in the sunlight. I mean, but most of the sunlight goes through if it's good quality glass. And if it does get absorbed, it can heat up. Now, here's something interesting. We have infrared optics, right? We have these night vision goggles and night viewing, night vision systems. We put them in our military gear, and anybody can use it. The optics that we use are not made of glass; they're made of silicon. The same kind of silicon that you use in your computers. And so silicon crystals are transparent to infrared, but they're opaque. They'll absorb visible light. All right, so silicon will be heated up a lot in sunlight, but the infrared will pass right through, and it'll come to a focus. If you shape it right and make a lens with it and stuff, it'll focus it and stuff like that. And that's how the night vision goggles work. So, for instance, your skin will stop some UV photons, and that's how you get sunburn. That's how some people get skin cancer. And even the astronauts on the surface of the moon need shielding. Matter of fact, they need a lot of shielding up there because there's no atmosphere on the moon. When the Apollo astronauts, when they landed, they had their rockets firing to slow them down. When they took off to go back to Earth, they fired their rockets again, their rocket motors again, and all those exhaust fumes from the rocket motors, that was the entire atmosphere of the moon, and only for a few hours, because most of that stuff will go off back out into space. There's zip zap of an atmosphere on the moon, and for that reason, every single photon from the sun blazes straight on in. All right, and that's a lot of ultraviolet, and actually the sun produces X-rays too. Now we're protected from a lot of that by our atmosphere, but not the astronauts. And theoretically, the sun deposits 1,370 joules per second on every square meter of Earth that's facing into the sun. Okay, so if you go up, like at the space shuttle at the equator of the Earth, and you take a, so the front of this table here where the document cam is, that's maybe almost a square meter. All right, so two of these together might be a little bit more than 1 square meter. So every square meter. Now it can't be a solar panel that's tilted toward the sun. It's got to be facing the sun. So you want to find the sun and then aim your solar panel right so that it catches, it's exactly perpendicular to the sunshine. And then 1,370 joules per second. And that's an enormous amount of energy that's dropped onto our atmosphere on the day side of the Earth. Now, on the night side of the Earth, of course, we don't get jack. We get a little starlight, but that's nothing. That's not even a spit in the bucket compared to the SUN. So, anyways, 1,370 joules per second. You know what that's called? The solar constant. Astronomers call that the solar constant. 1,370, and it varies a little bit. Plus or minus a few joules per second, depending on that. The sunspots on the sun, if there's a lot, then you don't have quite as many. And speaking of the astronauts, spacecraft and satellites also have to be protected from solar heat gain. It's an interesting, if you ever watch that movie Apollo 13, they talk about, on their way to the moon, they put their entire spacecraft into what they call a barbecue roll, very slow roll. so that they don't get, if they don't roll it, like once every 5 minutes or something, it's pretty slow, it'll get baked on one side and freezing on the other side. So they basically roll it. So they're going like a bullet in a gun. A bullet in a gun goes like this. It's from a rifle, anyways. It's spiraling, and so they were kind of spiraling as they went very slowly to the moon, so that they could, manage their solar heat gain. Okay, so here's another picture of the Apollo astronaut. And this is a nice picture because it shows, the gold visor on the front of the Apollo astronauts. Yeah, they had to have gold visors so that they didn't totally get blinded by the sun. And they had to land. And if you look at that, look how long those shadows are. That's towards sundown or maybe soon after sun up. I don't know which one, but definitely either soon after sun up or almost to sundown when the shadows get long. That's the only time that they can go up there, unless they have, totally protective devices and stuff. Now here's the opposite of that. A rooftop solar collector, you want solar heat gain. So you want as much transparency as you can until it gets into those water in the tubes. I guess what that's filled with is water. All right. Now, solar heat gain. Here's a picture of SR-71 Blackbird. Now, these are retired, they say. The fastest plane in the Air Force inventory. It's a reconnaissance plane, a spy plane. They can fly it over Russia, and the Russians can't do jack. It's flat wherever they want. Take pictures of Boris Putin's left earlobe if they want. And this is a picture of it landing. They got that chute. You know what other planes have chutes like that? The space shuttle. So this thing and the space shuttle are about the only planes that require chutes to stop. And I saw one of these things once. I was out watching. Do you ever go out and look at meteor showers, like in the summer? Now, meteor showers, they're best to view after midnight. And so one time I was out in Montana, beautiful clear night, looking at the Perseid meteor showers. And I was, so I had a poncho out in the soccer field, and I was looking up, and just it was nice, and you see the meteors coming by, but all of a sudden I saw this kind of reddish shaped V flying from the northwest to the southeast, and it was about 4 a.m. It was really early in the morning, and I thought to myself, oh, that's a flock of geese heading south for the winter, and they're so far up that they're catching rays of sun, and that's what I'm seeing. And so I thought, oh, cool, Montana, cool, nice, flock of geese. So then I dozed off and fell asleep and woke up again and watched more meteorites coming in. And I saw the exact same thing going from southeast back to northwest. I thought, what the heck is this? They changed their mind? And then I said, oh my God, it's a UFO. And so then eventually I went home and had breakfast. And the next day I went to talk to my thesis advisor, and God rest, he's now deceased, God rest his soul. I said, Doc, I saw a UFO last night, and I described it to him. And he's up there looking like, shaking his head like, yeah, okay, kid, what an idiot, UFO, right, yeah, good, nice, fine, right, get back to work. But then, one of my classmates was out, and he heard me describing it, and he said, you know what that was? He said it was probably the SR-71. Because the SR-71, they had just taken it out of retirement, and they were deploying it for something over in the Middle East. And so they were training in the United States. And he said, you know what that is? The SR-71, it flies so fast, the leading edges get red hot, just like the space shuttle. And so when they're training at high speed, it's going to look red hot if you're at night. You won't see it during the day, but at night, yeah. So that thing, So that's pretty cool. Anyway, so let's talk about the flow of energy and the whole idea of thermal equilibrium. In other words, we have the three heat transport modes. So heat can go from one thing to another if they're not in thermal equilibrium. So let's try to get that idea. All right, now recall, stirring up water, kinetic energy leads to an increase in temperature. Good. So two objects at different temperatures, they're not at thermal equilibrium. They don't have the same average kinetic energy. So if the temperature of X in this little blob here is less than the temperature of Y, then thermal energy will flow into X out of Y. If substance Y has a higher average kinetic energy, that means it's got stuff that's a little bit faster. All right, so there's a lot of fast molecules migrating out of X or out of Y and into X. So you have a big amount of kinetic energy net from Y to X. So that's going to cool down Y. That's going to lower the average, right? So it lowers the temperature. But you still have stuff kind of rotating over here from X to Y. It's not like it's banned for life. It'll move. But those things on average are slower. So they don't get there as fast, and they don't bring as much energy. So that is another thing that lowers the average kinetic energy of Y. So Y cools off, and X is getting a whole lot of, on average, higher kinetic energy stuff from Y, you know, molecule by molecule, so its temperature is going up. All right? Now, eventually, the temperatures will even out. You know, the temperature of Y will go down a little bit, the temperature of X will go down a little bit. And then eventually the temperatures will be the same, and what that means is the kinetic energy swapping is the same strength from Y to X, from X to Y. Right? So that's why those two arrows now, the two orange arrows, are the same color. All right, so when the temperature of X is equal to the temperature of Y, and they're in thermal contact in this example, then we would say that they're in thermal equilibrium. In other words, there's no net kinetic energy movement from one to the other. All right, there's a net movement from Y into X until all the temperatures are awake. Oh, did I say wake up? Because people on the aisle that are sitting there nodding off in class, give her a bump. Salam. You awake? Right in front. Good morning. Welcome. You ready? Don't fall asleep. I've been watching the last 5 minutes. Just kind of doozing off there. Anyways, when the energies are the same, kinetic energies average the same, thermal equilibrium. All right. Now, my final comment to you is heat melt heat is a brain burner, but you guys did pretty good on it today. So it's only kind of a semi-brain burner. But there's another one coming up, and I'm going to start you with it this weekend, and that is how to calculate the equilibrium temperature when two substances at two different temperatures are in thermal contact. I'll start you with that this weekend, and then next Tuesday we'll bring it all the way home. All right, you're dismissed, and now you can go to sleep for a few minutes if you want, or I'll see you guys next week.